Hello, my name is Mike Buller, and this video explores some of the fundamental principles relating to structural analysis and design. Consider a simply supported beam spanning between a pin support and a roller. The beam has two cantilevers, one to either end, and is subject to a uniformly distributed load and a triangular load, both acting over the same portion of the beam, two vertical point loads and one inclined point load. You should know that from your previous studies, a simply supported beam such as this has three unknowns associated with it. In this case, we have a vertical unknown to the pin support and also a horizontal unknown. Similarly, to the roller, we have just a vertical unknown. That is your three unknowns associated with a simply supported beam. You should also know that from your previous studies, we have three equations of equilibrium that must be satisfied for the beam to be statically determinate. These are the sum of the moments equals 0, the sum of the horizontal actions equals 0, and the sum of the vertical actions equals 0. It is clear that as we have three unknowns associated with the beam supports and three equations of equilibrium, that this particular beam is statically determinate. Once we've decided this, we can then go on and construct the free body diagram. The first part of this is to construct a line that represents the beam. To this, we then add our vertical supports. So we have a vertical action at the pin and a vertical action at the roller. We also have an unknown horizontal action at the pin. The next step would be to add the vertical loads. We have a UD load and a triangularly distributed load acting over part of the beam. Additionally, we have a vertical point load to the left-hand cantilever. Note the direction, this is acting upwards. We also have a vertical point load acting at the end of the UD load. And lastly, we have an inclined point load acting to the end of the right-hand cantilever. Again, note the direction of the inclined point load. The final step in constructing the free body diagram is to add the dimensions and the magnitude of the loads. Now we have the free body diagram. The first step in calculating the vertical and horizontal reactions is to resolve the inclined point load to the right-hand cantilever to its vertical and horizontal components. The point load acts at 45 degrees to the beam, so we can say that the vertical component PV equals the horizontal component PH, and these equal the magnitude of the load, so that's 25 kilonewtons, divided by the square root of 2. So both the horizontal and the vertical components of the point load equal 17.7 kilonewtons. We should at this stage state our assumptions when calculating the vertical and horizontal reactions. We're going to assume that vertical actions acting upwards are positive, horizontal actions acting from left to right are positive, and moments acting in a clockwise direction are again positive. So we can say that pH, the horizontal action associated with the inclined point load, is positive 17.7 kilonewtons. If we are going to maintain static equilibrium in the horizontal direction, we can write the sum of the horizontal forces equal 0. And from there we can say that HA plus the horizontal action associated with the point load, so that's pH, equals 0. This implies that HA plus 17.7 equals 0. Therefore, HA has to be minus 17.7 kilonewtons. That is, that it acts in an opposite direction to the horizontal action associated with the point load. Once we have resolved the forces horizontally, we can then go on and calculate the vertical reactions associated with the support at A and also the support at B. So in this instance, we are going to take moments about A to resolve the vertical force associated with the support at B. So we can write, again referring to our equations of equilibrium, we can write the sum of the moments at A equals 0. We are going to assume that everything acting in a clockwise direction is positive. If we firstly consider the UD load, we have a UD load with a triangular load effectively sitting on top of it. So we can consider those individually. If we have the support at A and a portion of beam, and to this portion of beam is firstly the 6 kilonewton load. It's not all the way along, it's only a partial load. Additionally, we also have a triangular load on top of it. So we can consider these two separately. Firstly, we'll consider the UD load. That has a magnitude of 6 kilonewtons per meter. So we can write plus, because it is positive, i.e. it is going clockwise about A. So point A is here. This UD load is acting in a clockwise direction. It is trying to rotate the beam in a clockwise direction about A. So we can write 6 times 3.2, that's the distance over which it acts, times its lever arm, 3.2 over 2. And you should know by now that the lever arm for a universally distributed load is taken from the centroid of the load. That's where the resultant action acts, and the lever arm is that distance from the point we're taking moments about to the centroid of the load. So that takes care of the uniformly distributed part of the load. To this we can add, so it's plus, because again this portion of being the triangular portion of the load is acting in a clockwise direction about A. And to calculate the forces associated with it, firstly we need the area of the triangle. So it has a length of 3.2 meters. And the magnitude of the load here, so effectively the height, if we're thinking about the area of the triangle, is 16, and that's in kilonewtons per meter. So that's your 22, as originally stated in the question, minus the 6 associated with the UD load. So 22 minus the 6 gives you the 16 kilonewtons a meter. The area of the triangle is half the base, so it's 3.2 over 2, times the height, that is 16. That effectively gives you the total load associated with that triangle. We now multiply that by the lever arm over which it acts. And the lever arm, as you should know for a triangle, the centroid of a triangle is 2/3 of the base. So that is 2/3 of 3.2. That is your lever arm associated with the triangle. So we can write 2/3 times 3.2. And that is the moment associated with the triangular part of the UD load. Once we have those, we can now consider the point loads. So firstly, we consider the 50 kilonewton point load, and again we take point A, we have a length of beam with your 50 kilonewtons acting on it. That is also trying to rotate the beam in a clockwise direction about A, so again it is positive. So we've got plus 50 times its lever arm, which is 3.2 meters. Then if we consider the point load to the end of the beam, so this is the vertical component of the inclined point load. Again, it is acting clockwise about A, so we have 17.7 times its lever arm, which is the total length. So we have A, we have a point load acting out here, its lever arm is this distance here, so that is 17.7 kilonewtons. Again, it is acting in a positive direction, and the lever arm is 8.85 meters. And the last load we have to consider is the point load to the left-hand cantilever. And again, if we consider point A, we have a portion of beam. Notice it's going the opposite direction, so we have A here. We have the point load is acting vertically up. It is also going clockwise. It is trying to rotate the beam in a clockwise direction about A. So again, we can write plus, and that's 60 kilonewtons is the magnitude of the load times the lever arm, 1.2. And the last bit of this, we have the vertical reaction at B, again taking moments about A, that acts in a negative direction, so it's minus VB times 6.1. And all of that, as per our original equation of equilibrium, all of that has to equate to 0. If you go on and then simplify that, you should find that 474.9 minus 6.1 VB equals 0. That means that VB equals 77.8 kilonewtons. That is our vertical reaction associated with the roller support at B. The last part of this problem is to solve the vertical reaction at A. So we can write the sum of the vertical forces equals 0. Therefore, it's fair to say that VA plus VB minus the sum of the point loads minus the sum of the UD loads equals 0. You should bear in mind that we have assumed initially that everything acting vertically up is classed as being positive. That's something to bear in mind whilst you are resolving the vertical actions to get VA. So if we start putting some numbers into this, we've got VA, that is the unknown, that's what we're after at the moment, plus VB, we've calculated that already, 77.8. That is acting vertically up, so it's positive, minus the sum of the point loads. Now we have 2 point loads acting down, so therefore they would be negative. That's the 50 kilonewtons, so it's minus 50. We also have the vertical component of the inclined point load, so that's plus 17.7. Those two are both acting down, so they are negative. The point load to the left-hand end of the cantilever is acting vertically up, so that is positive. Going back to our original assumption, we assumed that loads acting up are positive, so it's plus 60. And then we can take into account the UD loads. So it's minus, first of all, the rectangular portion, 6 times 3.2. That's the magnitude of the load times the distance over which it acts. And then also the triangular portion, it's 3.2 over 2 times 16. Effectively, half base times height. So it's half the base times the load gives the total load associated with that portion of the triangle. And again, to satisfy our equations of equilibrium, all of that equals 0. If you go on and resolve that, you will get that VA plus 25.2 equals 0. That gives VA equals minus 25.2 kilonewtons. Now this makes complete sense that it's negative. If we go back and have a look at our free body diagram, we assumed first of all that the vertical reaction at A was acting vertically up. The negative sign for the calculated value means that our assumption was wrong. So in essence, VA is actually acting vertically down. And if you look at the magnitude of the loading, again, that makes sense. So we have a vertical force holding the beam down effectively. And if we, as I say, if we consider the magnitude of the loading, you have 60 kilonewtons here on the end of the beam. That is effectively trying to lift the beam. So in order to oppose that, it would make sense that we have a vertical force acting down, trying to hold the beam down. This problem is now complete, as we have resolved the vertical and horizontal reactions associated with the pin at A and the roller at B. I hope you have found this video useful. If you have any comments or suggestions, please do send me an email at the address shown on screen. Thank you for watching.